ground detectors hear the chirps, space will hear the bass. That is the simplest way I can describe the next great turn in our listening to the universe. On Earth, the Laser Interferometer Gravitational Wave Observatory and its partners have tuned our ears to bright, quick birdsong bursts at tens to thousands of hertz as stellar mass black holes collide. But out in space, far from the tremor of winds and oceans, we are preparing an instrument for the long, low notes, the millihertz waves that roll on for months and years, born when the biggest black holes in the cosmos circle and finally merge. This observatory is called the Laser Interferometer Space Antenna LISA, and it will change the soundtrack of the universe. Why speak about it now? Because in late January of 2024, the European Space Agency formally adopted LISA, moving the mission from elegant drawings and careful studies into full implementation, real hardware, real contracts, real work. The National Aeronautics and Space Administration confirmed a partnership providing key flight elements, telescopes, lasers, and charge management devices under a memorandum process that followed the adoption. And in mid-June of 2025, ESA and the prime contractor OHB signed the agreement to build the 3 spacecraft, marking the start of industrial construction for a launch currently expected in the mid-2030s. It is no longer a what if, it is a thing being built. To understand what LISA will hear, it helps to think in octaves. Ground-based interferometers are superb in the audio-like band from roughly 10 Hz up to a few thousand Hz, where the final seconds of compact object mergers sing as bright chirps. Space opens the deep octaves below. LISA is designed for waves from about 0.1 MHz up to about 1 Hz. These long waves come from much wider orbits and far heavier systems, and they are completely swamped on Earth by seismic and atmospheric gravity gradient noise. Hence, we must fly the detector. So the move to space is not an extravagance. It is a physical necessity to hear the bass. How do you build an ear for such low notes with geometry and patience? LISA is a triangle of 3 drag-free spacecraft separated by about 2.5 million kilometers, trailing the Earth around the Sunday. Laser beams run along each side of the triangle, comparing the separations between free-falling gold-platinum test masses. As a gravitational wave passes, it rhythmically stretches one arm and squeezes another. The lasers record this dance as minute changes in distance. The constellation slowly cartwheels as it orbits, scanning the whole sky and improving the localization of sources over time. It is a musical instrument the size of a solar system chord. The science is as grand as the instrument. LISA will listen to extreme mass ratio inspirals, small dense objects like stellar mass black holes orbiting and spiraling into supermassive black holes 1,000,000 times the mass of the Sunday. These systems can spend years in band tracing intricate paths through warped space-time and allowing exquisitely precise tests of Einstein's theory in the strongest fields we know. LISA will also capture the great slow crescendos of supermassive black hole mergers, when galaxies collide, events that shape the growth of structure across cosmic time. And closer to home, tens of thousands of compact binaries in our own galaxy will form a rich, steady foreground from which LISA will resolve a veritable menagerie of verification binaries and map the hidden stellar graveyard of the Milky Way. We are confident LISA can do this, because we have already flown the essential physics. LISA Pathfinder, a small European spacecraft launched to prove the concept, demonstrated that free-falling test masses could be shielded and controlled so well that the residual acceleration noise was not merely within requirements, but significantly better, with performance improving as the craft outgassed and settled. In plain terms, we know how to create near-perfect stillness around a test mass in space, and we know how to measure its motion with astonishing precision. That stillness is the canvas on which LISA will paint its symphonies. There is another quiet revolution here: multiband astronomy. Some binaries that LIGO and Virgo catch at high pitch in their final seconds would have been audible to LISA months or even years earlier, murmuring at low frequency while slowly tightening. That means early warnings, accurate merger times, and sky patches delivered in advance so that telescopes can be poised ready to watch the moment of coalescence across the spectrum. The promise was outlined soon after the first detection in 2016, and it is now a central part of the LISA vision: bass preludes in space leading to treble crescendos on Earth. But I do not think of this as mere coordination between observatories. The deeper idea is that the universe is not a static picture, it is a score. A supermassive black hole pairing 2 dark stars of gravity in a galactic core will hum in LISA's band for a long season. Over that season, the phase of the wave carries a biography, mass spin, eccentricity, the geometry of space-time itself. We will fit models that thread those data, and in doing so, measure how black holes grew with their galaxies when they met, and how violently they merged. In a very literal sense, we will take a stethoscope to the hearts of galaxies. So when I say space will hear the bass, I am not being poetic, I am being precise. We are building a triangle millions of kilometers wide to sense waves 1,000 to 1,000,000 times lower in frequency than those we have already heard from the ground. The adoption is signed, the roles are agreed, the first industrial contracts are in place. The stage is set for the deepest notes yet recorded from the cosmos. And that brings us to the practical question that fascinates me most as a physicist. How exactly do you fly a ruler 2.5 million kilometers long and keep it steady enough to hear a ripple smaller than an atom? Because the answer to that question begins with drag-free flight and ends with light itself, with drag-free flight and with light. Imagine placing a tiny cube no thicker than a couple of finger joints at the heart of a spacecraft and asking the universe to cradle it. In laser interferometer, space antenna's language, that cube is a gravitational reference, a gold-platinum test mass, 46 millimeters on a side, and about 2 kilograms in mass, floating inside its own vacuum enclosure. The spacecraft's first duty is almost parental do not touch. Instead, it watches the mass with exquisitely quiet capacitive sensors and flies around it using microthrusters to cancel every whisper of solar pressure or thermal twitch, so that the cube falls freely along the pure geodesic of the spacetime. We know this works because we flew it. LISA Pathfinder proved that we can keep such masses in near-perfect freefall and measure their relative motion with stability far beyond the original requirement, an achievement that turned a bold idea into an engineering practice. The way you do not touch in space is with force measured in millionths of a Newton. On Pathfinder and in the LISA architecture, micro-Newton propulsion systems nudge the spacecraft with the gentlest of breaths. NASA's Space Technology 7 Disturbance Reduction System flew electrospray colloid thrusters that could whisper thrust with astonishing smoothness. In flight, they held the craft centered on its free-falling masses, with nanometer precision in the millihertz band. It is a lovely reversal of intuition. The masses are not bolted to the spacecraft. The spacecraft is steered around the masses. That is drag-free control, and it is the stillness on which the rest of the instrument depends. Even perfect freefall is not enough. The masses charge up under cosmic ray bombardment, gathering a few stray electrons that can tug on them. LISA's answer is to bathe the test masses in ultraviolet light, allowing the photoelectric effect to bleed off excess charge and keep electrostatic drifts at bay. Pathfinder demonstrated discharge with mercury lamps. The flight system for LISA advances this with compact ultraviolet light, emitting diodes smaller, more robust, and miserly with power. It is a quiet housekeeping, but essential gravity must be the only hand on the mass. Now to the light in laser interferometer space antenna. Across each 2.5 million kilometer side of the triangle, a small telescope launches a faint, exquisitely stable laser beam. At the far end, another telescope receives it, and we beat the incoming light against a local laser to form a heterodyne tone, an audio-like signal whose phase encodes the separation between the distant test masses. You might picture it as three enormous slanted violins exchanging long, steady notes. What we actually read out is the relative phase of those notes with a phasometer, an instrument that must resolve microcycles of phase in the presence of million-cycle laser noise. That is not theatrical flourish, it is the job description, but the orchestra pit is moving. The triangle trails the Earth around the sun, the distances breathe, the Doppler shifts slide the beat, notes up and down by megahertz over the year. On Earth, interferometers calm laser frequency noise by making their two arms equal. In space, the arms are always unequal and always changing. So LISA performs a piece of digital magic called time delay interferometry. We time tag every phase measurement and later combine them with precisely chosen delays that mimic an equal arm Michelson. Done properly, the algorithm cancels the huge common mode laser frequency noise and leaves the tiny differential signal, the gravitational waves slow stretch and squeeze. This is the heart of LISA's metrology turn-changing geometry into a virtual equal arm, and the baseline emerges from beneath the hum. There is a further finesse. Each spacecraft carries its own ultra-stable clock, and any jitter in those clocks leaks into the phase. LISA's links carry special clock tone sidebands that let us measure and then subtract the clock noise from the science data. In simulations and lab demonstrations, this procedure pushes clock noise below the requirement, even as the beat notes wander with Doppler shifts. It is rather like sending a metronome click along with the music to align the bar lines before you listen for the melody. Laser stability begins before any subtraction. The plan blends layers, pre-stabilize each laser to an optical cavity, then use arm locking, which treats an inter-spacecraft arm itself as a grand reference to follow the slow, long-term stability of the constellation. Recent work shows that hybrid schemes, combining cavity and arm references, can push residual frequency noise down by orders of magnitude and ease the burden on the time delay interferometry. In other words, you tune the instrument first and only then rely on the clever mathematics to polish away the last hints of drift. How do you keep the beams aligned across those millions of kilometers while everything is moving? Each spacecraft carries a pair of off-axis telescopes to transmit and receive. Because light takes many seconds to cross an arm, the transmitter must point ahead, aiming not at where a partner spacecraft is now, but where it will be when the light arrives. A dedicated point-ahead angle mechanism tilts the outgoing beam by a tiny programmable amount. Acquisition and fine tracking are then guided by star trackers and by the interferometer itself, which senses minute wavefront tilts and nudges, mirrors to keep the link clean. These are small motions with epic consequences. A few microradians of pointing decide whether the link lives or dies. All of this complexity exists for a simple physical reason: the waves we are after are slow and faint. Laser interferometer space antenna is tuned for ripples with periods of minutes to hours, roughly 0.1 MHz up to near 1 Hz, which is to say for orbits that take weeks to years to decay. Ground detectors cannot reach this band. The Earth itself is too restless. In space, with drag-free flight ultraviolet charge control arm locking and time delay interferometry layered together, the deep octaves open. The triangle cartwheels and orbits scanning the sky and slowly refining the positions of its sources over months. The longer it listens, the clearer the baseline becomes. And there is one more virtue to the slow music forewarning. Because the loudest supermassive black hole binaries and the intricate extreme mass ratio inspirals linger for so long in laser interferometer space, antennas band the phasing of their waves can be tracked in advance, turning gravitational wave astronomy into something like celestial weather. We will be able to say in so many weeks on this patch of sky, the crescendo will come and hand the baton to telescopes that watch for light and to ground interferometers that catch the final high-pitched tremor. That is multiband astronomy in the truest sense, a single event scored across octaves from space's deepest base to Earth's bright treble. And it sets up a question I love to ask next. What stories do those lingering, information-rich signals tell about the hearts of galaxies and the geometry of gravity itself? Once you learn how to read their bar lines and overtones over months and years, what stories do those lingering, information-rich signals tell about the hearts of galaxies and the geometry of gravity itself? Let me begin with the most intricate storytellers of all extreme mass ratio inspirals. Picture a small, dense traveler, a stellar mass black hole, or a neutron star caught by the gravity of a supermassive black hole in a galactic nucleus. It does not plunge straight in. It threads a rosette of orbits, slowly losing energy and angular momentum, and it will sing to the laser interferometer space antenna for months and sometimes for years. Because the small body samples space-time so intimately, its waveform becomes a cartographer's tool. Every precession, every flutter in frequency sketches the mass and the spin of the central black hole, and crucially the shape of space-time around it. In Einstein's theory, that shape is determined by only mass, and spin the no-hair statement and laser interferometer space antenna is built to test that with exquisite fidelity. The precision here is not hyperbole, it is the dividend of time. A source that remains in band for many orbits allows us to fit models to hundreds of thousands of waveform cycles. With sufficiently fast and faithful waveform families now arriving from the community, we can in principle measure the big black hole's mass and spin to well below the percent level and sift for tiny deviations that might signal environmental effects or cracks in our theory's armor. That is why there is such energy now in building fully relativistic templates for extreme mass ratio inspirals. The promise of laser interferometer space antenna is only as sharp as the models we carry to meet it. There is astrophysics nestled inside those deviations too. Galactic centers are not tidy places. There are stars, stellar black holes, sometimes gas, sometimes even a second supermassive black hole. Each of these can leave fingerprints on the inspiral, from gentle drags to sudden resonances. By tracking the slow evolution of the orbit and the harmonics in its radiation, we can infer not only the properties of the central black hole, but the character of its surroundings, the density cusp, the presence of a disk, perhaps the tug of a hidden companion. In that sense, extreme mass ratio inspirals become deep core biopsies of galactic nuclei. Now turn to the grand crescendos mergers of supermassive black holes when galaxies collide. These are the bass drums of the universe. Their waves are loud in the millihertz band, and most usefully for the rest of astronomy, they grow in amplitude and sweep upward in pitch over weeks to months. That slow cadence means forewarning. As parameter estimation tightens, laser interferometer space antenna will issue alerts that say, in effect on this patch of sky around this date, the final bars will play. This gives electromagnetic observatories time to organize campaigns and to watch the stage as the merger unfolds. The concept has been explored for years and is now moving into practical low-latency strategies, fast detection pipelines, evolving sky maps, and triggered follow-ups as the coalescence nears. Why chase light from black holes that by definition shine? Not at all, because the systems around them can be incandescent. A circumbinary disk may flicker or reconfigure as the binary tightens. Jets might precess or flare. After the merger, the remnant's recoil can shock gas and light it up. Even simple variability, if it is correlated with the gravitational wave phasing, becomes a smoking gun anchoring a host galaxy, and with it a redshift. That combination, gravitational wave distance plus electromagnetic redshift, is the essence of a standard siren. It lets us place a point on the cosmic expansion curve without relying on the traditional distance ladders. Laser interferometer space antenna brings standard sirens to the era of massive black hole assembly, opening a new rung on the cosmological ladder. There is a deeper historical question in those mergers. Where do the biggest black holes come from? One school argues for heavy seeds born in the young universe from collapsing gas clouds. Another favors lighter seeds that grow through many successive mergers and accretion episodes. The population of mergers that laser interferometer space antenna hears their masses, spins and redshifts will discriminate between those formation channels. In the most optimistic models, we may even listen back toward the time when the first structures assembled, taking a direct census of how the dark hearts of galaxies were built. Even without a flash of light, the gravitational waves themselves tell a sweeping story. The spins of the two black holes, imprinted in subtle modulations of the phase, reveal how the pair came together. Aligned spins hint at a long, steady courtship in a disk. Misaligned, tumbling spins suggest a more chaotic meeting in a crowded nucleus. The final ring down, the brief aftertone as the remnant settles, acts as a spectroscopic line for spacetime, a chorus of quasi-normal modes, whose frequencies and damping times must match the predictions for a Kerr black hole. Measure more than one of those tones and you have a clean test of the no-hair theorem with nothing more than gravity's own music. All of this rests on the practical power of pre-merger localization. As the constellation cartwheels and the waveform evolves, parameter correlations break and the error ellipse shrinks, often dramatically in the final days. In some scenarios, the sky area can fall to the scale of a few tens of square degrees before coalescence, especially when spin precession is strong. That is a target a wide field survey can tile, and it transforms supermassive black hole mergers from serendipitous discoveries into scheduled multi-messenger events. And then there is the census that only a space observatory can compile the rate and distribution of these mergers across cosmic time. Combine laser interferometer space antennas counts and parameters with models of galaxy growth, and you can test whether mergers or accretion dominate black hole mass buildup in different epochs. Fold in extreme mass ratio inspirals, and you gain the local demographics of the nuclear star cluster, the mass function of the small bodies that feed the giant, and hints of mass segregation near the event horizon. With enough detections, even population-level quantities like the slope of the black hole mass function become measurable by gravitational waves alone. So the stories are many precision tests of gravity's architecture, biographies of galactic cores, a new rung on cosmology's ladder, and a map of how the universe built its central engines. But there is a final challenge before any of that is realized. The millihertz sky is busy. The Milky Way itself fills the band with a broad, steady chorus from myriad compact binaries, and the very richness that makes laser interferometer space antenna scientifically intoxicating also makes the data analysis a high art. Disentangling overlapping sources, subtracting foregrounds, and stitching together month-long threads into coherent narratives. That is where we must go next. how you read a crowded score without losing the soloist, and why laser interferometer space antenna will be as much a triumph of data analysis as of engineering. So how do you read a crowded score without losing the soloist? I think of the millihertz sky as a galactic choir. Most voices are pairs of white dwarfs, stellar embers going round and round on orbits of minutes to hours. There are so many of them that at low frequencies their songs blur into a soft confusion, limited haze, a raised floor of sound that sits above the instrument's own noise. This foreground was predicted long ago and refined with modern population models. It will dominate roughly around the half millihertz octave, precisely where space is most revealing and Earth is most deaf. The point is not that the foreground is a nuisance. It is that the foreground is a measurement of how many compact binaries live in the Milky Way and how they are distributed. We will have to model it to hear anything else, and in doing so we will learn about our galaxy's hidden graveyard. In practice, we do not remove a noise, we fit the whole chorus. The laser interferometer space antenna community has spent years rehearsing on synthetic skies the mock LISA data challenges, from the early Radler galaxy sets to the newer Sangria, precisely so we can pull out individual lines from a crowd. Global fit pipelines slide through the data week by week, identify bright notes, subtract them, then cycle again as fainter voices emerge. In those exercises, after about 1 year of listening, as many as 10,000 ultra-compact binaries can be resolved as discrete sources, while the residual wash beneath becomes a population observable in its own right. That is how you separate melody from harmony in a universe that refuses to sing solo. The algorithms are not esoteric ornaments, they are the instrument. Transdimensional Bayesian samplers that can turn parameters on and off as sources appear and fade, fast time, delay interferometry, simulators that let us generate millions of signals in seconds, clever stage searches that use what you learned this month as a prior for next month's data. These are the tools that turn a crowded spectrum into a catalogue. Even neural density estimators and other machine learning methods are now joining the repertoire, not to replace physics, but to accelerate it, guiding the sampler toward plausible valleys in parameter space. Alongside the anonymous multitude are the named voices, the verification binaries. These are compact systems already known in light, with orbits so tight that their gravitational wave strains are guaranteed to be heard early in the mission. Some were on the list nearly 2 decades ago. In the last few years, Gaia's exquisite distances and new time, domain surveys have expanded and sharpened the set. A recent compilation using Gaia's 3rd data release elevates roughly 18 systems to verification status and identifies a further few dozen as strong detections within the mission lifetime. When those tones appear at the expected frequencies and amplitudes, they will be the first hello telling us the triangle is working as designed. A favourite of mine is the eclipsing double white dwarf ZTFJ1539 plus 5027, an orbital period of under 7 minutes, the shortest known. It is not dramatic in the way of colliding black holes, but it is wonderfully useful. The geometry is pinned by eclipses, the decay is driven by gravitational radiation, and the prediction for the laser interferometer space antenna is crisp. Others like HM Cancri or V407 Vulpeculae round out a small choir of calibration stars. There is something quietly thrilling about this. Before we hear the universe's deepest mysteries, we will check our ear against a set of familiar tuning forks. All of this rests on how we represent the data. On the spacecraft, we measure inter-spacecraft phases along each arm. On the ground, we braid those streams into time, delay interferometry combinations that cancel laser frequency jitters by orders of magnitude. From those braids, we create nearly orthogonal A, E, and T channels, 2 exquisitely sensitive to astrophysical signals and 1 much less so. That quasi-null channel is not wasted. It carries information about instrumental noise and helps validate any claim of a diffuse background. Choosing the right set of combinations is not mere bookkeeping. For stochastic backgrounds, in particular the channel geometry and overlap functions, decide how well you can separate sky signal from instrument and from the galactic foreground. And yes, beyond the resolvable choir, we will listen for an even softer music stochastic backgrounds from the early universe. If the very young cosmos underwent symmetry-breaking phase transitions, or if networks of cosmic strings formed, they could have left a broad, stationary hum in precisely this millihertz band. The laser interferometer space antenna alone can set incisive bounds. In partnership with sister constellations Taiji or Tianqin, correlated analyses improve sensitivity and help untangle components. In some forecasts, the network can push constraints, or even make a detection where a single constellation would struggle. The millihertz sky, in other words, is not only a map of our galaxy, it is a microphone pressed against the early cosmic furnace. There is a lovely reciprocity here. The same techniques we use to subtract the galactic foreground global fit's hierarchical inference are precisely the ones that will let any primordial background stand out if it is there. Conversely, a measured foreground becomes a new probe of galactic structure. Recent work has even shown how the ensemble of double white dwarfs acts as a set of accelerometers sensitive to the Milky Way's potential as they orbit and drift. The data analysis is not afterthought, it is astronomy by other means. I find it helpful to picture the first mission year. Early on, the verification binaries light up, giving us phase-locked beacons to check timing, pointing, and calibration. The global fit engines begin to comb the band, resolving the loudest few thousand sources and trimming down the confusion. Month by month, as the constellation cartwheels and the Doppler rhythm writes parallax into each tone positions, sharpen and parameter covariances break. By the end of that year, the catalogue swells into the 5-figure range, the residual galactic wash carries demographic information, and our sensitivity to faint diffuse backgrounds improves. We will have learned how to hear in millihertz. Then the real work begins, following sources across years, watching frequencies drift as orbits decay, and waiting for the low, slow swells that herald the approach of a massive black hole merger, which is where I want to go next. Once the choir is mapped and the score is clean, the long motifs stand out, the months-long crescendos of supermassive black hole pairs and the intricate embroidery of extreme mass ratio inspirals. In those waves are precise distances and sometimes host galaxies. Together they become standard sirens that let us chart the expansion of the universe at redshifts where other methods thin out. So let us leave the crowded hall for a moment and walk toward those grand slow duets, what they can tell us about cosmology and how a bass note measured in space can anchor the Hubble diagram far beyond where the candles will burn. So let us draw the cosmological map with sound. A standard siren is simply a source whose gravitational wave amplitude and phasing let us read off an absolute luminosity distance with no distance ladder calibration. We proved the principle 8 years ago when 2 neutron stars merged in the galaxy. NGC 4993 gravitational waves gave the distance. Light from the kilonova and the host galaxy gave the redshift. Together they drew a point on the Hubble diagram. Laser interferometer space antenna extends that idea to much larger distances and to the era when galaxies were building their central engines. The method is the same, but the orchestra moves to the lowest octave. In space, our best bright sirens will be supermassive black hole binaries, millions of solar masses whose slow crescendos can be tracked for months. Forecasts, using realistic populations, show that when a counterpart can be identified, laser interferometer space antenna distances paired with host galaxy redshifts can constrain cosmology well beyond the nearby universe, turning a sequence of mergers into a gravitational Hubble diagram at redshifts of order 1 and above. The details depend on astrophysics, the rate of mergers, the disk physics, and how often the systems announce themselves in light, but the path is clear: base note distances from space redshifts, from telescopes cosmology, from the duet. How do we actually find the light? 2 strategies are ripening. The first is archival. The Rubin Observatory's decade-long Sky movie will catalogue quasars by the 100 million. Among them will be a small cadre of periodically varying active nuclei, massive binaries already stirring the surrounding gas years before coalescence. When laser interferometer space antenna announces a gravitational wave source with a known sky patch and a known slow chirp, we can comb those archives for a periodic quasar whose period and evolution match the gravitational score. Simulations show that the true counterpart often stands out with a vanishingly small false alarm probability, especially because the gravitational chirp washes away spurious periodicities from quasar noise. The second strategy is real-time theatre. Because the constellation cartwheels and the waveform accumulates phase, localization improves as the merger approaches, sometimes to sky areas that a wide-field survey can tile in the last days to weeks. Decade-old theories sketch the timetable for such pre-merger targeting. Modern low-latency pipelines now demonstrate end-to-end methods for issuing early alerts from laser interferometer space antenna data, so that observatories can point in time for the final bars. If a network forms with a partner constellation such as Taiji flying in a different orbit, triangulation can squeeze the error contours even further. The practical message is that we will not be stumbling in the dark. We will be waiting under the right patch of sky as gravity counts down. Even when gas is quiet, the environment can matter. Magnetohydrodynamic simulations of circumbinary disks show that close to merger the binary can decouple from the flow. The disk may briefly fall out of step and then light up as it resettles, offering afterglow-like signatures. Longer-term disk torques can pump or damp eccentricity, tilt jets or imprint precession behavior that telescopes might catch, while laser interferometer space antenna traces the inspiral underneath. Each detection will be a case study. Not simply is there light, but what kind of disk did this pair inhabit, and how did gravity talk to it? Of course, not every merger will flash. When no counterpart appears, we are not helpless. We switch from bright sirens to dark sirens using galaxy catalogs inside the laser interferometer space antenna localization volume to assign statistical redshifts. The method has already delivered Hubble constant measurements on ground-based events. For space, new work is building the machinery to take a census of galaxies in each three-dimensional error volume and fold that into the inference. It is not as sharp as a single named host, but across many events the statistics tighten. As always, we must be honest about systematics and selection effects. The community is quantifying those too. At higher redshift, another veil appears: weak gravitational lensing by the cosmic web. The same matter that structures the universe slightly magnifies or demagnifies the wave, blurring the distance. For bright sirens beyond about redshift 0.6, forecasts suggest that weak lensing often dominates the distance error budget. Delensing, estimating the magnification from galaxy shear maps or other probes, can help, but is challenging with present surveys. Recent studies caution that delensing gains may be modest unless future imaging becomes both deeper and sharper. A reminder that laser interferometer space antennas cosmology will be a partnership with the great sky surveys of the coming decade. There is a silver lining: lensing is not merely an obstacle but a probe. Wave optics and weak lensing effects on gravitational waves themselves carry information about the matter along the line of sight, allowing cross-checks with galaxy surveys and even tests of dark matter scenarios. In time, we may learn to treat the lensing pattern as part of the signal, not just an error bar. Put the pieces together and you glimpse a practical cosmology program. Laser interferometer space antenna provides distances for massive black hole binaries across cosmic noon. Rubin and Roman offer redshifts and periodicity histories. Pre-merger alerts marshal pointed campaigns for the final act, and statistical catalogs backstop the cases with no light. Even a handful of well-characterized bright sirens can check the cosmic expansion independently of the distance ladder. A population across redshifts can test the smoothness of that expansion, and in some scenarios, the transparency of gravity itself on large scales. This is not an alternative to other methods. It is a new geometric rung you can stand on while surveying the same horizon. And the engineering is on track to make it more than a thought experiment. The European Space Agency's formal adoption of laser interferometer space antenna in late January of 2024 moved the mission into implementation, with partners contributing lasers, telescopes, clocks, and control construction activities ramped through the middle of the decade toward a mid-30s launch. The next time you see an artist's impression of the triangle, imagine it not as an emblem, but as a calendar, a set of dates when the deepest bass notes of the universe will become measurable distances. But cosmology is only one promise of the millihertz sky. The same long information-rich waveforms that yield distances also test the architecture of gravity in its strongest fields through the no-hair overtones of ring-down and the fine structure of extreme mass ratio inspirals. They let us watch black holes grow with their galaxies one slow bar at a time. So with the Hubble diagram sketched in low notes, let us lean closer to the physics of the objects themselves, how spins, tides, and resonances write their signatures into months of data, and how a baseline can reveal whether space-time follows the score of Einstein or improvises ever so slightly on the theme. So when I say we can read these waves, what I really mean is that spins, tides, and resonances write legible punctuation into months of music. Begin with spin. Two black holes do not simply fall together. They dance with their own rotations, and those spins couple to the orbit. If the spins tilt, the orbital plane slowly wobbles, precession modulating the phase and amplitude in a way that only long, quiet listening can decode. In Einstein's theory, the final remnant must be a Kerr black hole whose spectrum of ring-down tones, the quasi-normal modes, is fixed entirely by its mass and spin. If we can hear more than one of those overtones, we can perform black hole spectroscopy, fit multiple lines in space-time spectrum, and ask whether they agree with the Kerr score. Laser interferometer space antenna sits in a sweet spot here. For the most massive mergers, it can record the slow approach and the final ring down, with high signal to noise turning a theoretical promised no-hair test via spectroscopic overtones into an observational program. Recent studies quantify how well LISA can do this in the millihertz band, and how to design agnostic and targeted analyses of deviations if the tones disagree. Extreme mass ratio inspirals add a subtler signature resonances. The small body's path around a supermassive black hole is governed by three fundamental frequencies: radial, polar, and azimuthal. As gravitational radiation drains energy and angular momentum, those frequencies drift. Every so often, two of them lock into a rational ratio. At such transient resonances, the conservative and dissipative pieces of the motion talk to one another in a new way, and the orbital elements jump slightly. The effect is not theatrical, but over hundreds of thousands of cycles it matters. If we ignore it in our templates, we bias the parameters. If we include it, the jump itself becomes a measurement of the space-time geometry and of any perturbing environment. This is precisely the kind of structure that LISA's years-long Emery observations will resolve, and recent modelling has developed the relativistic machinery to capture these resonant passages faithfully. Those same EMRIs are precision meters for the shape of space-time near a horizon. In general relativity, the multipole moments of a Kerr black hole are not free, they are locked to mass and spin. The prolonged multi-harmonic signal from a small body orbiting deep in the potential well lets us infer those moments directly. If even a tiny third moment or quadrupole deviation crept in months of precession and periastron advance would advertise it. Forecasts suggest that with sufficiently faithful waveforms, LISA can pin down central masses and spins to well below the percent level and place incisive bounds on any departures from the Kerr prescription. The accuracy grows from time in band, not just loudness. Tides and transfer tell another story at the lighter end of the band. The Milky Way's ultra-compact binaries, especially double white dwarfs, radiate steadily in millihertz, and some are close enough and tight enough that gravitational radiation alone drives their orbital evolution today. Where mass transfer begins, the phase evolution departs from the pure radiation reaction track, letting us diagnose whether matter is streaming through a Lagrange point, whether tides are heating the stars, and how magnetic braking and composition complicate the flow. Here, LISA's band is not a distraction from black holes. It is a laboratory for degenerate stellar physics, and the known verification binaries will act as early calibrators of those effects before the first massive mergers arrive. The millihertz octave is also where we can probe how gravity itself propagates. Over millions of kilometers and hours of flight time, any small change in dispersion, the idea that different frequencies might travel at slightly different speeds, would dephase the signal. Likewise, some Lorentz-violating theories predict frequency-dependent damping. Because LISA records long coherent tracks across a wide fractional bandwidth, it can bound such effects, cleanly complementing ground detectors and pulsar timing arrays in other frequency ranges. This is not a promise to break Einstein. It is a promise to test the rules he wrote with a ruler measured in light, seconds rather than kilometers. Spins themselves are a fossil record of formation. If a pair grew together inside a disk, their spins tend to align with the orbit. If they met chaotically in a crowded nucleus, their spins are often misaligned and tumble. In the millihertz band, the precessional modulations are slow enough to track cleanly, and for extreme mass ratio inspirals, the central black hole's spin drags spacetime, the famous Lentz-Thirring effect, imprinting a long baseline compass into the waveform. By reading those modulations, we reconstruct not just what is there now, but how it likely came to be an origin story, encoded in the phasing of gravity's music. And there is a population-level dividend. Each Emery adds a bead to the necklace of black hole demographics: the mass distribution of supermassive black holes in the nearby universe, the mass function of the compact objects that feed them, and the degree of mass segregation in nuclear star clusters. Simulations suggest that even on conservative assumptions, the mission should resolve at least a handful of Emerys per year, with optimistic channels yielding very many more. In either case, the aggregate constrains slopes and normalizations of those hidden populations. It is hard to exaggerate how new that is, a census of stellar corpses in the very center of galaxies taken with gravity alone. All of this rests on the simple physical fact that LISA listens at low frequency and for a very long time. Its triangle measures waves from roughly 0.1 millihertz up to around 1/10 of a hertz, a band inaccessible on Earth because the planet itself is too restless. In that band, orbits evolve slowly, precession cycles unfold over weeks, resonances have time to act, ring downs from truly massive mergers sing long enough to fit cleanly. The instrument's design, the unequal arm interferometry, the time delay combinations, the drag-free flight exists to open that octave. It is not just a different detector, it is a different regime of nature, and the physics it accesses is correspondingly rich. So in the months before a supermassive coalescence, you can imagine what the data will look like on a screen in the mission operations room, a slow, rising tone wobbling gently as spins precess, a faint, almost step-like change as the orbit slips through a resonance. Then at last, the brief, pure overtones of ring-down, the space-time bells struck and fading. From those features we will read masses and spins, map multipoles, test dispersion, and when a counterpart appears, place another point on the Hubble diagram. It is gravity as biography, not a single number, but a life story reconstructed from rhythm and harmony. And because this is a human enterprise as much as a scientific one, the triumph will come from preparation, the waveforms, the pipelines, the calibration stars we will use to tune the ear. In the next part, I want to step through one of these narratives, end to end, follow an extreme mass ratio in spiral, as it first murmurs in the noise, then brightens into a named source, and finally writes its epilogue in overtones, so that when we speak of hearing the deepest bass, you can picture exactly how that score is read note by note. Over seasons of listening, let me walk you through one of these tales, end to end, the life of an extreme mass ratio in spiral, as we would meet it in the laser interferometer space antenna's band. First, the murmur. Somewhere in a quiet galactic nucleus, a stellar mass black hole, think tens of suns, has wandered deep into the grip of a central giant, a million or so solar masses. It does not plunge. It settles into a bound, lopsided orbit that skims close to the horizon and then swings far out again. 3 natural clock beats govern the motion: a radial beat as the orbit breathes in and out, a polar beat as the orbit tips above and below the equatorial plane, and an azimuthal beat as it threads around the hole. Because Einstein's gravity is curved and twisted by the central spin, those 3 beats are not commensurate. Their interference paints a waveform rich in sidebands, whose phasing depends cleanly and deterministically on the big hole's mass, its spin, and the exact path taken by the small companion. That is why these sources are such powerful cartographers of spacetime. In the beginning, the signal is faint, only a little above the steady galactic foreground, and we learn to hear it the way a musician picks out a single viola line in a crowded orchestra by coherence. We match the data against families of fully relativistic templates that encode those 3 fundamental frequencies and their slow drift as gravitational radiation drains energy and angular momentum. Modern waveform engines built on black hole perturbation theory and the Tucholsky equation accelerated on graphics processors, even aided by surrogate fits, and machine learning now generate months-long multi-harmonic tracks, fast enough for searches. They include the key self-force physics that corrects a geodesic into a true inspiral and thus keep phase with the sky for hundreds of thousands of cycles. Week by week, as the constellation cartwheels and the orbit evolves, the parameters tighten. The slow precession of the orbital plane length-stirring precession writes a gentle amplitude and phase modulation that tells us the sign and size of the central spin. The periapsis itself precesses splitting power into sidebands, whose spacing is a ruler for mass and compactness. Because laser interferometer space antenna sits in the low frequency octaves from roughly 0.01 MHz up to about 1 Hz, the inspiral lingers and time is converted into accuracy mass and spin sharpened from rough sketches into measurements at well below the percent level in favorable cases. Then something subtle can happen: resonance. As radiation reaction nudges, the 3 beats too may slip into a simple ratio for a brief passage. At that moment, the serene adiabatic drift breaks and the orbital elements jump by a tiny definite amount. It is not a dramatic crash, it is a finesse note. But if we do not include it in the template, the phasing will run off and the parameters will be biased. The theory of these transient resonances has matured from first principles to detailed modeling. They are a unique signature of strongly curved spacetime and a diagnostic of any gentle tugs from a surrounding stellar cluster or disk. By the middle of the mission year, the source has a name in the catalogue and a biography on our screens. Global Fit pipelines honed on the Mock-Liza data challenges and now running as multi-source graphics accelerated engines keep the whole sky in view, subtracting bright galactic binaries, refitting the instrument noise, then returning to the inspiral to add the next fortnight of data. It is not a single detection, but a season of listening. With each refresh, the sky position tightens. With each refresh, the spin, precession imprint becomes crisper, and practical questions begin to take scientific shape. What is the slope of the compact object? Mass function in the galactic center is the big hole's quadrupole. Exactly what Kerr predicts. Is there any sign of a second body in the core under the bonnet? This works only because the templates have caught up with the physics. A decade ago, we spoke of Kludge's ingenious hybrids that sketch the right harmonics. Today, fully relativistic models exist for generic, inclined, mildly eccentric orbits, with adiabatic self-force driving and frequency domain fluxes computed by Tucholsky solvers. New formalisms are pushing toward higher orders in the self-force to keep phase fidelity across the entire inspiral. The arc is clear. What began as proof of concept waveforms is becoming a library precise enough to test the hairless simplicity of Kerr. Near the end, the music quickens. The radial turning point creeps inward toward the last stable orbit. The sideband forest thickens. Precession speeds up. If the central hole is rapidly spinning, frame dragging can be so strong that the orbital plane precesses many times over the final months, and that motion is not ornament, it is information. Fit those modulations well, and you read off the spin vector and the mass with extraordinary precision. Fit them poorly, and you learn immediately that your model is lacking because the residuals grow coherent. This is one of the great virtues of long, low-frequency listening. The data will tell you when the theory is not good enough. At last, the solo fades. The small body crosses the separatrix. The harmonics shut down like lights at the end of a concert. And if the orbit was prograde and close to equatorial, a brief ring-down of the central object may be audible in the millihertz band. That aftertone, the quasi-normal modes, has discrete frequencies and damping times fixed entirely by the remnant's mass and spin. Measure more than one tone and you have black hole spectroscopy, a direct test of whether the remnant is described by the Kerr solution, or whether there is the faintest hint of improvisation in gravity's score. Laser interferometer space antenna is designed to make such measurements for massive mergers. In favorable geometries and distances, the loudest extreme mass ratio captures may also leave a measurable after ring. Fold many such biographies together, and population physics emerges. Event rates remain uncertain not because of the instrument, but because nature's funnels into galactic centers are varied. Conservative modeling finds at least a few extreme mass ratio inspirals per mission year. Optimistic channels triggered, for example, by a second supermassive black hole stirring the nuclear cluster yield of order 10 or more per year. Any tally will be transformative. Each detection is a weighed and spun supermassive black hole. Each detection samples the hidden symmetry of stellar mass corpses that have mass segregated into the central parsec, and all the while the verification stars nearby, ultra-compact binaries already known in light, keep us honest. Their steady notes, anchor timing, calibration, and response. When ZTFJ1539 plus 5027, the 7-minute eclipsing double white dwarf, comes up exactly where and how it should, we know that the ruler in space is reading true. When HM Cancre's 5-minute cycle is resolved, we know we have the ear for the millihertz band. They are the tuning forks we strike before we listen for the deepest mysteries. So that is the arc, a whisper teased from a crowded choir into a named source, resonant punctuation captured and decoded, a final cadence read as a test of gravity's architecture. In the next movement, I want to widen the lens to the other monarchs of the millihertz sky, the supermassive black hole binaries whose months-long crescendos we will track to scheduled coalescences, and then show how those deep base distances paired with light become points on a Hubble diagram written in gravity's hand. So let's widen the lens and sit with the monarchs of the millihertz sky, the great pairs of supermassive black holes drifting toward coalescence in the hearts of merging galaxies. Their song is long and low. It begins as a lazy undulation months of nearly even bars, and then as the orbit tightens, the pitch rises and the rhythm quickens. I love this because it means we can live with a system for a season. We do not merely catch the last gasp. We keep company with it, watch its parameters sharpen, and if the cosmos is kind, warn astronomers that the final chords will play on a certain patch of sky on a certain week, with time to open their shutters. In recent forecasts, practical pipelines that treat the laser interferometer space antenna's data as evolving spectrograms can raise such alerts and even predict the merger time, transforming a distant catastrophe into an appointment in our calendars. Those alerts grow more precise as the constellation cartwheels and the waveform accumulates phase. The geometry writes a slow Doppler dance into the signal and correlations between distant sky position and inclination break. By the last fortnight, some binaries collapsed to sky areas that a wide-field camera can plausibly tile, and in favourable cases, the unique counterpart can be picked out a week or more before coalescence, with vanishingly small odds of confusion. That is not wishful thinking. It is the result of targeted counterpart studies that work with realistic light curves and real survey cadences. The practical message is simple. We may not just hear the bass, we may see its stage, setting in light in time. What kind of light? If there is a circumbinary disk, the gas can modulate as the pair tightens, and it may briefly decouple and then re-brighten after the merger. Even without a final flare, the years before coalescence can leave a telltale heartbeat, a slow shortening of a quasi-periodic signal as gravitational radiation steals orbital energy. The Nancy Grace Roman Space Telescope's high-latitude time-domain survey and the ground-based Rubin Observatory's Sky movie are expected to contain precisely this class of quasar, periodically varying, then subtly chirping as the period shrinks. When the laser interferometer space antenna names a patch of sky and hums the right baseline, you can comb those archives for a quasar whose timing matches gravity's score. In simulations, the genuine host tends to stand out cleanly. With a counterpart in hand, you have a standard siren. Gravity gives you an absolute luminosity distance. The host galaxy's spectrum gives you a redshift. Together they place a point on the Hubble diagram. Recent work shows that a population of such bright sirens in the millihertz band can carry cosmological weight reaching to redshifts of order unity and above, well beyond the reach of nearby standard candles. It will not replace other methods. It will check them on different systematics in a different epoch of the universe. That is how a discipline matures. You add new rungs to the ladder and see whether they sit level with the old. What if the merger hides its light? Then we move from bright sirens to dark sirens, statistical cosmology. You take the laser interferometer space antenna's three-dimensional error volume and fill it with galaxies from deep surveys. You weight each one by how plausible it is as a host, and you let many such events accumulate into a measurement. The precision per source is modest, but the average tightens. It is a patient path, and it pairs naturally with another quiet revolution, a network. If a sister constellation such as China's Taiji flies in a different orbit, correlated listening can sharpen localizations, and for cosmology, reduce distance scatters so far that sub-percent Hubble parameter constraints become plausible in optimistic scenarios. Gravity's geometry improves when heard in stereo. Rates are the honest uncertainty. How many supermassive black hole pairs will sing loudly enough in the laser interferometer space antenna's band during the mission? Astrophysical models disagree, and that disagreement is precisely what makes this exciting. Whatever we hear will teach us how galaxies built their central engines. New population studies fold in realistic survey strategies and counterpart efficiencies to forecast how many bright sirens we might secure for cosmology and how many will travel dark. The numbers vary, but the through line does not. Even a small set of well-characterized mergers can test the expansion history independently of the distance ladder. A larger set turns base notes into a map. The physics encoded in these months-long crescendos is richer than a single distance. Spins leave slow readable modulations. Eccentricity and its damping speak to how the pair formed. And the final ring down, those quasi-normal overtones that fade like a struck bell off a black hole spectroscopy. Measure more than one tone, and you ask a clean, thrilling question. Does the remnant match the Kerr solution of Einstein's theory, or is the universe improvising just a little on his theme? The millihertz band is ideal for this because truly massive mergers ring slowly and loudly enough to fit multiple modes. That is not poetry, it is a measurable plan. All of this only matters if we can act in time, and that is why early warning pipelines and low latency parameter estimation have moved from whiteboards to code. Teams now demonstrate end-to-end schemes that watch the time delay interferometry spectrograms trigger on rising power and update merger time posteriors as the weeks tick down practical steps that turn a future coalescence into a scheduled multi-messenger campaign. I find that quietly astonishing, the idea that we might tell you next Thursday the heart of a galaxy will change state and then watch in radio and X-rays and optical light as gravity writes the final bar. There is a deeper dividend hidden in these slow baselines formation histories. If spins arrive mostly aligned, we will infer long disk-assisted courtships. If they tumble at wild angles, we will favour chaotic dynamical pairings in crowded nuclei. If eccentricity survives late, gas may have been scarce. If it damps early, disks may have been thick. In other words, supermassive black hole mergers are not merely rulers for cosmology, They are diaries for galaxy growth written in precession and phasing, and overtones across months of listening. That is a different kind of knowledge, explanatory, not just descriptive, and it is the gift of the millihertz band. And when the last bars do play, the aftertone is more than a coda. The remnant can recoil as gravitational waves carry linear momentum. If gas is present, that kick can shock a disk and light it anew. If a jet is anchored, its precession may change. Every one of these behaviors becomes a cross-check on the gravitational inference light, not as a crutch, but as a second measurement of the same event. We will learn to orchestrate these campaigns to move across octaves from space's deepest bass to Earth's bright treble with the calm cadence of a well-rehearsed score. So picture the first of these scheduled coalescences, a gentle swell noticed months out, a narrowing patch of sky, a community quietly aligning telescopes, and then the moment itself, gravity's wave lifting and falling as space-time settles. In the next part, I want to step behind the scenes and show you how such a merger week might actually unfold in the mission room. The data products we will watch, the alerts we will send, and the way the laser interferometer space antenna turns light seconds of geometry into a clock you can plan around. And so as the last graphs fade from the mission room screens, I like to step outside, if only in the mind's eye, and stand beneath an ordinary night. The constellations are familiar, but the feeling is different now that we have learned to listen. Somewhere high above the reach of weather and stone, a quiet triangle of spacecraft is keeping time with the long, slow tides of gravity, measuring the hush between stars for the rise and fall of distant monarchs. It is a simple image light shared across great distance, comparing the beat of one corner to the next, and yet it contains the whole idea that space itself can be a score, and that we can read it if our instrument is steady and patient enough. What we will hear is not spectacle so much as biography. A year-long swell that tells you the weight and spin of a black hole as plainly as the curve of a signature. A faint hesitation where an orbit lingers in resonance. The clear bell-like overtones of a space-time settling into its final form. These are not fireworks. They are the slow punctuation marks of a universe that writes in seasons and centuries, and the only way to catch them is to meet them with a similar calm. That is the promise of a detector that listens in millihertz, a vow to trade urgency for depth, to let truth arrive at the pace set by the cosmos rather than by us. And I find comfort in the craft as much as in the science. We learned how to cradle a tiny cube of metal and watch it fall with nothing but gravity for company. How to hold a spacecraft around it like a cupped hand steering on whispers, so faint that sunlight itself felt clumsy by comparison. That quiet engineering triumph, proving we can make stillness in space, was the first note of this symphony, and its echo remains in everything to come. From there, the story broadens. Ground observatories will go on catching the bright, quick birdsong of stellar collisions. The spaceborne ear will hum along to the deep bass lines beneath. Together, they turn individual events into movements, scored across octaves. A low prelude in space, a high finale on Earth, and sometimes a flash of light to mark the turning of the page. We will set our calendars to mergers in distant galaxies and watch as gravity keeps its appointments. We will thread population into principal origin, into law, until the expansion of the universe, the growth of its black hearts, and the architecture of its geometry all sit on the same stave. But the image that stays with me is smaller. It is the triangle cartwheeling, gently measuring distances that scarcely change and yet change just enough. It is the idea that between sunlit dust and planetary orbits, there is a place quiet enough to hear the slowest notes the universe plays. There is humility in that, an admission that we must leave the ground to reach the deepest silence, and that silence itself is the medium of discovery. So let us leave it here, on a night like any other, with the sky untroubled and the instruments waiting. Somewhere, a supermassive duet is beginning to lean toward its cadence. Somewhere else, a smaller companion is patiently tracing the geometry near a horizon, line by line, as if copying a manuscript written in curvature. And here for a moment we stand between them at human scale, holding the thought that these immensities can be known not all at once, but surely if we listen long enough and with care. Ground detectors hear the chirps, space will hear the bass. This would be our benediction. The bright, quick notes will continue, but in the years ahead the background will deepen, the stave will lengthen, and the melody will relax into something older and more complete. When it does, we will be ready to read it. The triangle will be in place, the light will be steady, and the long notes will arrive from the dark with the unhurried confidence of tides. And if as you look up you feel that gentle widening that comes, when a familiar sky acquires a second meaning, when stars become not just lights but landmarks in a sea of quiet motion, that I think is the best part of all. The universe has always been singing. We have only just learned which notes to lean into and which silences to keep.